There is a machine in millions of homes that has been storing and releasing energy for 300 years without a single battery. You wind it up and a weight rises. The weight falls slowly, and that falling weight powers the whole thing for a week. Grandfather clocks are gravity batteries, and the same principle now holds most of the stored electricity on this planet. I'm going to show you exactly how that works. Why the largest battery humanity has ever built contains no chemistry at all. Why it will still be running in 50 years when every lithium battery on Earth today has been thrown away, and the honest reason almost nobody knows it exists. I'm also going to tell you, with the actual numbers, why you cannot build one of these in your garage. Because that is the part every video on this subject leaves out. Let me start with the clock, because everything else is just this idea made larger. Open the case of a traditional weight-driven clock, and you'll see a heavy brass cylinder hanging from a chain or a cord wrapped around a drum. When you wind that clock, you are doing physical work with your arm, lifting that weight up against gravity, and that work does not disappear. It is stored in the position of the weight, held there, waiting. Physicists call it gravitational potential energy, and the important thing about it is that it stays exactly where you put it. The weight then descends, extremely slowly, and as it falls, it turns the drum, which drives the gear train, which moves the hands. The escapement, which is the ticking mechanism inside, exists purely to release that stored energy in tiny, evenly spaced portions, rather than letting the weight crash to the bottom in 2 seconds. So a grandfather clock is a device that takes 30 seconds of human effort and releases it steadily over 7 days. That is a battery in every sense that matters, and it has no chemistry inside it whatsoever. Now here's why that idea scales so beautifully. The energy stored in a lifted object comes down to 3 things, which are how heavy it is, how high you lift it, and the strength of gravity. Gravity is fixed, so you have exactly 2 levers to pull, which are mass and height. Make the object heavier or lift it higher, and you store more energy. And there is no upper limit to that except engineering. Which raises an obvious question, and it is the question that built the largest battery on Earth. What is the heaviest thing you could possibly lift, and how high could you lift it? The answer, it turns out, is a lake. This is pumped storage, hydropower, and it works with a simplicity that borders on absurd. You build 2 reservoirs, one high on a hill or mountain, and one down in the valley below, and you connect them with enormous pipes running through a powerhouse. When electricity is cheap and plentiful, usually at night or during a windy afternoon when the grid has more power than it needs, you use that surplus electricity to run pumps that push water from the lower reservoir up to the higher one. That water now sits at the top of a mountain, and it is holding every bit of that energy in its position. Then, when demand spikes and the grid needs power urgently, you open the valves and let that water fall back down through turbines, which spin generators and put electricity straight back onto the grid. Water up is charging, and water down is discharging, and the mountain is the battery. And the business model behind it is beautifully simple, because the plant buys electricity when it is cheap and sells it when it is expensive. Power at 3 in the morning costs a fraction of what power costs at 6 in the evening. So a pumped storage operator is essentially running an arbitrage on time. You lose a portion of the energy in the round trip, and you still come out ahead, because the price difference between the middle of the night and the evening peak is far larger than the losses, which means these plants have paid for themselves for a century on nothing more complicated than the fact that electricity is worth different amounts at different hours of the day. Now here is the fact that genuinely surprises people the first time they hear it. Pumped hydro accounts for roughly 90% of all grid-scale energy storage in the world today, not lithium and not any chemical battery technology, because the overwhelming majority of stored electricity on this planet is water sitting in a reservoir on a hill. There is a facility in Bath County, Virginia that holds over 3 gigawatts of generating capacity, which for years earned it the nickname of the world's largest battery. It is 2 lakes and a tunnel, and it can put more power onto the American grid than most power stations can, on demand, in minutes. And it does a second job that almost nobody outside the industry ever hears about, which is keeping the grid stable moment to moment. An electricity grid has to balance supply and demand continuously, second by second, because if they drift apart, the frequency shifts and equipment begins to fail. A pumped storage plant can respond to that within seconds, ramping up or backing off to hold the balance, And that responsiveness is one of the most valuable services on the entire network. Some of these plants are also capable of what engineers call a black start, which is the ability to restart from nothing after a major blackout without needing power from elsewhere. That matters more than it sounds, since most large power stations cannot start themselves and need external electricity to get going, which creates an obvious problem when the entire grid is down. A reservoir full of water needs nothing but an open valve. So, in a genuine national emergency, gravity is the thing that gets everything else running again. And this technology is not new, because the first pumped storage schemes were built in the Alps in the 1890s, using surplus power at night to lift water for use during the day. That means engineers solved grid-scale energy storage over a century ago, using nothing but water, pipes, and gravity, and we have been quietly relying on it ever since. And there is a specific reason so many of these plants exist in the first place, which has nothing to do with renewable energy. Through the middle of the 20th century, countries built large coal and nuclear power stations. And those stations have an awkward property, because they run most efficiently at a constant output, and they do not like being turned up and down. But human electricity demand is not constant at all, since it collapses in the middle of the night and spikes in the early evening when everybody arrives home and switches things on. So utilities faced a genuine problem, which was enormous surplus power at 3 in the morning and a shortage at 6 in the evening. Pumped storage solved that exactly, since the surplus night power ran the pumps and lifted the water. And the evening peak was met by letting it come back down, which means most of the world's pumped hydro was built to serve coal and nuclear plants. Decades before anyone was worried about intermittent solar, and it turned out to be perfectly suited to a job nobody had imagined yet. So let me put this properly against lithium, because the comparison is genuinely striking, and it runs in both directions. The first advantage is degradation, or rather the complete absence of it. Every chemical battery you have ever owned dies slowly, because the chemistry inside it changes with every cycle. And your phone battery after 4 years holds noticeably less than it did on day 1. A grid lithium installation is typically expected to serve for somewhere around 10 to 15 years before it needs replacing, and it loses capacity throughout that time. A reservoir does not degrade, because a lake full of water at the top of a hill holds precisely as much energy on its 10,000th cycle as it did on its first. There is no chemistry to wear out, since the only things that age are the pumps and turbines, and those are ordinary machines you can service and replace. Which leads to the second advantage, which is lifespan. Pumped hydro facilities are built to operate for 50 to 100 years, and there are plants running today that were commissioned before most of us were born. Think about what that actually means in practice, because a lithium installation built this year will have been replaced 4 or 5 times over before a pumped hydro plant built. This year reaches the end of its life. The third advantage is materials, and this one matters more every year. A gravity battery contains water, concrete, steel, and machinery. It requires no lithium, no cobalt, no nickel, and no rare earth elements, which means no mining for those materials, no complex global supply chain, and no fire risk, because water at the top of a hill cannot catch fire. The fourth advantage is scale, since pumped hydro can store staggering amounts of energy for many hours, and the grid needs exactly that kind of endurance to smooth out the gap between when solar and wind produce power and when people actually use it. So the obvious question is why we are not building these everywhere. And this is where I have to be completely honest with you, because the disadvantages are severe, and they are the entire reason lithium exists in this conversation at all. The first problem is geography, and it is brutal. You need 2 large reservoirs with a substantial height difference between them, close enough together to connect, on ground, stable enough to hold them, near enough to the grid to be useful. That is a very specific piece of landscape, and most of the world does not have it, which means you cannot build a pumped storage plant where you need one, since you can only build it where the mountain already is. The second problem is cost and time, because these are enormous civil engineering projects that require tunneling through rock and building dams, costing billions and taking the better part of a decade from approval to operation. A container of lithium batteries can be delivered on a truck and switched on in months, and in a world that wants results before the next election, that difference matters enormously. The third problem is environmental and social, because flooding a valley to create a reservoir changes ecosystems, alters rivers, and sometimes displaces people. And modern permitting reflects all of that. Many of the best sites in developed countries were built decades ago, and getting approval for new ones today is genuinely difficult and often takes longer than the construction itself. There is one promising route around that, which engineers call closed-loop pumped storage. Instead of damming a river, you build two artificial ponds that are not connected to any natural waterway, and you simply move the same water back and forth between them forever. That removes most of the ecological objection, since no river is blocked and no fish migration is interrupted, and it opens up sites that would never be approved otherwise, including old quarries and open-pit mines that already have a deep hole and a flat top. The fourth problem is efficiency. Since a pumped hydro system returns roughly 70 to 85% of the energy you put into it, because you lose some in the pumps, some in the turbines, and some to friction in the pipes. A modern lithium battery does noticeably better than that on a round trip, and for some applications, that gap is decisive. And the fifth problem is the one that ends the argument for most uses, because a gravity battery cannot move. You cannot put a reservoir in a car, or a phone, or a laptop, or a cordless drill. Since those things need energy dense enough to carry, and that is a job only chemistry can do. So the honest picture is not that lithium is a mistake, because lithium won the applications where you need to carry your energy with you, and it won them fairly. Gravity storage is unbeatable when the energy can stay in one place forever, and chemistry is unbeatable when the energy has to travel. Which brings me to the question in the title, and the answer is more interesting than a conspiracy. Nobody forbade this, and nobody buried it, because pumped hydro is running right now at enormous scale in dozens of countries, holding up grids that would otherwise fail. What actually happened is that it became invisible. There is no consumer product here because you cannot buy a pumped hydro plant, and no company will ever advertise one to you during a football game. The plants themselves are usually built in remote mountain country where nobody drives past them, and they were mostly commissioned decades ago, which means there is no ribbon cutting and no news cycle. Meanwhile, lithium is in your hand every single day. It is in the car advertisement, it is in the phone launch, and it is the technology every article about the energy transition is written about. One technology sells products to individuals, and the other is a piece of national infrastructure that quietly does its job in a valley. And that difference explains the entire gap in public awareness. It is not that the knowledge disappeared, since every power engineer on Earth knows this, and it is that the public conversation about batteries was shaped by the industry with something to sell you. Now let me show you the part of this story that is happening right now, because engineers have been trying to solve the geography problem for the last decade. The obvious idea is to stop using water and to lift something solid instead. One approach uses enormous cranes to stack heavy composite blocks into a tower when there is surplus power, and then lowers those blocks back down through the same motors when power is needed, with the motors running as generators on the way down. Another approach uses disused mine shafts, which is genuinely elegant, because a mine shaft is a deep vertical hole that somebody else already paid to dig. You hang an enormous weight on a cable in that shaft, winch it up with surplus electricity, and let it descend to generate power, and there are thousands of abandoned shafts across old industrial regions. A third approach uses heavy rail cars on a steep slope, hauling them uphill with surplus power and letting them roll back down. The appeal of all three is that they work almost anywhere since they do not require two lakes and a mountain, and they still keep the core advantages of no chemistry, no degradation, and no fire risk. But let me be honest about where these stand, because the internet is far more excited about them than the results currently justify. These are early-stage technologies, and some high-profile projects have struggled to demonstrate the economics at scale, while pumped hydro has a century of operating history behind it. The physics is sound, and the engineering is real. And whether any of it competes on cost against a falling lithium price is a question that has not been answered yet. So watch this space with genuine interest and hold your enthusiasm until the numbers arrive. Now the section that matters most for anyone watching this thinking about their own home, because this is where I have to disappoint a lot of people with maths. Gravity storage does not work at household scale, and the reason is not engineering, and it is not regulation, because it is arithmetic. Let me give you the actual number. Take a mass of 1,000 kilograms, which is a full ton, and lift it 10 meters straight up, which is roughly the height of a 3-story building. The energy you have just stored is about 27 watt-hours. 27 watt-hours will run a laptop for perhaps 20 minutes. Your home probably uses somewhere around 20 to 30 kilowatt-hours in a day, which is around 1,000 times what that ton of concrete just stored. So, to store a single day of household electricity using gravity, you would need to lift roughly 1,000 tons by 10 meters, or 1 ton by 10 kilometers. And neither of those is happening in a back garden. This is precisely why pumped hydro uses lakes and mountains, since the only way to make gravity storage useful is to work at a scale that is genuinely enormous. And it is why every home gravity battery you have seen promoted online is either quietly tiny or quietly not real. If you want to store energy at home, chemistry wins, and it wins by a factor of about 1,000. That number is also the best possible answer to the question of why we do not simply build gravity batteries everywhere, because the honest answer is that they only make sense when you can find a mountain. Now let me come back to where we started, because the small-scale version of this idea did work for centuries, and it worked because the energy required was tiny. A clock needs almost nothing, since moving a set of hands against a little friction is one of the least demanding mechanical jobs there is. So a weight of a few kilograms, descending a meter over a week, is genuinely enough. And that is why weight-driven clocks were the most reliable timekeepers in the world for hundreds of years. The same logic applied across a great deal of pre-industrial machinery, since weight-driven mechanisms powered turnspits in kitchens, drove automata and music boxers, and provided steady, controlled force in workshops where an even unvarying motion mattered more than raw power. And there is a related idea that ran the industrial world for 1,000 years before electricity, which is the water wheel. A mill on a stream is using exactly the same physics, since water that fell as rain on high ground is descending under gravity, and the wheel intercepts a portion of that descent and turns it into rotation. The mill is not storing energy because it is harvesting it in real time, and the source is identical. That is the thread running through this entire story, from a clock weight to a millstone to a lake on a mountain, since it is all the same simple transaction of lifting something up and getting the work back when it comes down. Let me put the current situation in perspective, because there is a real reason this matters right now. The central problem with solar and wind is not generating the power, since we have become very good at that, and it is that the sun sets and the wind drops at times that have nothing to do with when people cook dinner. Which means the entire transition to renewable energy is, in practice, a storage problem. You need somewhere to put the surplus from a sunny afternoon so it can come back out on a still evening, and you need it at a scale that keeps a country running. Lithium does this well for a few hours, and it is being deployed at enormous scale to do exactly that, and its price has fallen dramatically. Pumped hydro does it for far longer, for decades on end, and it does it with a lifespan no chemical battery can approach, which is why countries with the right geography are actively expanding it, and why old sites are being upgraded and brought back into service. So the future is almost certainly both, since batteries handle the fast, short, portable jobs, and gravity handles the slow, enormous, permanent ones. The mistake is only in thinking that the newest technology must be the one that wins everything. Let me answer the questions I know are coming. Does gravity storage really account for most of the world's storage? Yes, since pumped hydro represents roughly 90% of grid-scale storage capacity globally, and it has held that position for decades. Why does it not degrade? Because there is no chemical reaction involved. Since the water is not consumed or altered, and it is simply moved up and moved down, so the only wear is in the mechanical equipment. How efficient is it? Round-trip efficiency is typically somewhere in the range of 70 to 85%, which is lower than lithium, though it is offset by a lifespan several times longer. Can I build one at home? No, and the arithmetic above is the reason. Since the energy stored by lifting realistic household masses is trivial compared to what a home actually uses, what about the block stacking and mineshaft systems? They are real engineering projects that solve the geography problem in principle, and they are early stage, so their economics at scale remain unproven. How long does a pumped hydro plant last? 50 to 100 years is the design expectation, and there are plants operating today that were built in the first half of the 20th century. Why is nobody talking about it? Because it is infrastructure rather than a product, so there is nothing to sell you. Nobody advertises it, and most of it was built before anyone watching this was paying attention. So here is the whole of it. The oldest and largest battery technology on this planet has no chemistry in it at all, since it works by lifting something heavy and letting it fall. It runs your grandfather clock for a week on 30 seconds of winding, and it holds roughly 90% of the world's stored grid electricity in the form of water sitting on top of hills. It does not degrade, it lasts for a century. It contains no rare metals, and it cannot catch fire. It also cannot move. It needs a mountain. It takes a decade to build, and it stores so little at small scale that a ton of concrete lifted 3 stories will not run your laptop through lunch. Nobody forbade it, and nobody buried it, because it simply became invisible, doing its job in remote valleys while the conversation about batteries was written by the industry that had something to sell to individuals. So tell me down in the comments whether you have ever seen a pumped storage plant or whether there is one in your part of the country, because most people live closer to one than they realize. And if you own a weight-driven clock, tell me about it. Since you are the owner of the oldest form of energy storage still in daily use, I read every single one. Next time, I'm going to show you the machine that pumps water uphill continuously, day and night, using no electricity, no fuel, and no solar panel. Invented over 200 years ago and still running on farms today, subscribe so you don't miss it. And remember that the most important technologies are usually the ones nobody is trying to sell you.